Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to Module 5. And in the last few modules then, we have talked about this thermoelectric effect, and we have discussed the role of electrons. Of course, like throughout this course, we have generally focused on electrons. And as you know, the current is given by this expression. And we had also obtained an expression for the heat current carried by electrons. And from all of that, we obtained expressions for the Seebeck coefficient and the conductance and the heat conductance due to the electrons. And the point I made in the last module is that a major part of the heat conduction in a real solid comes not from the electrons, but from phonons. Now, what do you mean by phonons? The basic idea is you take any solid, and if you're looking at very low temperatures, then you can say all the atoms are frozen in place. So they're right where they are, they don't move. That's the picture we have at low temperatures. Now, once you raise the temperature, there's always a little thermal energy. So these things are jiggling around. And the amount they jiggle increases with temperature. So the more you raise the temperature, more they're jiggling around. And in fact, the picture people have is that once they're jiggling quite a bit, in the sense that each one moves almost an atomic distance between one atom and another, that's when a solid melts. It's jiggling so much that basically it melts away. And that's the melting point. Now, usually, of course, we are working with solids that are way below their melting point. And so each thing is just jiggling around a little bit. And this is roughly what you think of in terms of phonons, that the phonons kind of describe that energy, that jiggling energy. Okay? And the low frequency phonons are in a way like what you might call acoustic waves. You know, an acoustic wave is one like when you have a solid and you tap it at one end. And what happens is when you tap it there, atoms are jiggling, and that energy then propagates down the thing. And so these phonons then are basically almost like these acoustic waves that are going along. It's just that at room temperature, there's a lot of this kind of energy already in there, even though you haven't actually tapped it, it's just already in there. These things are all jiggling around, see? And if you heat up one side of a solid compared to the other, what that means is on this side, atoms are jiggling a little more because it's hotter. And so that extra energy of jiggling then gets transmitted down the chain to the colder side where the atoms are not quite jiggling as much. So that's this heat conduction by phonons, which is what we want to describe. Now, question is, if you look back at what we have done with electrons, the question we are asking is, how do we modify this to describe the heat conduction by phonons? Okay. Now, let me first write this expression for the conductance that we had earlier. So, if you remember, conductance was written as, and maybe I'll just write it here, that quantity was this Q squared over H times m lambda divided by L plus lambda. So if you remember, the way we were thinking about this is the quantum of conductance, m is the number of phonons, number of modes of the electrons, lambda is the mean free path, and if you're looking at ballistic samples, that means L is 0 and the lambda cancels out, and this is the usual ballistic conductance. But then if you're looking at long samples, you can drop the lambda, and in that case you have like Ohm's law. So this was the expression I had before, so let me insert that into this description. So we'll have this Q squared over H, and there's a 1 over Q, so I could write it as Q over H. And instead of this expression here, I'll put m lambda over L plus lambda. Okay, and this is all electrons. Now the question is, how do I write down the heat current? This is the charge current carried by electrons. And what we want to write is the heat current carried by phonons. And of course, in this course, this is largely about electrons. This is the only module where I'll be talking about phonons. So I'm not really doing justice to the topic, in the sense we are not really talking at length about phonons and doing it properly. What I wanted to show you was how the viewpoint we have discussed in this course can be extended in a fairly straightforward way to all kinds of other things. In fact, a lot of this work about heat conduction due to phonons, the approach that I'll be telling you about, that was developed in the mechanical engineering community, kind of almost independent of, that was something that we didn't know all that much about. But then when we looked at it, we realized that it was really very closely related to what we were doing with electrons. And that's what I'm trying to describe to you in this module. So the way it would work is, firstly, that just as in your contacts, the electrons are distributed according to the Fermi function, F, that we have talked about before, that's this function. The phonons in your contacts are distributed according to the Bose function. And this is what I'll write as N. Maybe I'll write it over here. So have this for reference. So this is the number of phonons at a given energy h bar omega is given by 1 divided by and for comparison, you see the Fermi function we had been working with that I had written there looks something like this. This was the Fermi function that describes electrons. That's given by this. Okay, and so this, of course, I'm stating just as I more or less kind of stated the Fermi function. That is, we didn't really go into any serious discussion of this. I tried to rationalize it, saying that, well, it's kind of reasonable from simple arguments. But of course, a proper discussion of this needs us to talk a lot more about this general subject of equilibrium statistical mechanics. And that is something we do towards the end of the next course. So the part 2 of this course, I do talk a little more about it so you get a better feeling for where these functions come from. But as far as this course is concerned, these are things I'm asking you to just accept. Namely, Fermi function tells us how electrons are distributed in energy. Bose function tells us how phonons are distributed in energy, this h bar omega. And this also applies to photons. And the reason there's the difference, there is this, of course, very key difference of minus and plus. And that makes these functions look totally different, actually, if you looked at it. And the difference is electrons obey the exclusion principle. So when you have a state, you can only put one electron there. You cannot put two. Whereas when it comes to phonons or photons, the picture people have is when you have a state, you can have many, many phonons or photons in that mode. In fact, for example, I mentioned acoustic waves earlier. Acoustic wave would be a case where at a given frequency, you have millions of phonons in that mode acting in a coherent way, so you actually have a measurable acoustic wave. Okay. So there are many subtle differences there, which one can talk at length about. But for today's discussion, then I'm saying, let's accept that there is a function like this for phonons, just like there was a Fermi function for electrons. And the thing is, we got two reservoirs with two different temperatures. So just as previously we had written F1 minus F2, now we can write N1 minus N2. Let me use a red pen so see the difference with that one clearly. So this is N1 minus N2. That's it. So instead of Fermi functions, we now have the Bose functions with the two different temperatures. And we're trying to write the energy, the IQ, energy that is carried by phonons. Okay. Now, electrons, every time they go through, they carry a certain amount of charge Q. So whereas what we are trying to figure out is the energy carried by phonons. So when we try to translate this here, what we should do is something like this. You see, if we just wrote this down, it would be Q over H integral. Instead of energy, we could write dH bar omega. And then we could have m lambda over L plus lambda for phonons. So this is what would happen if I just translated it. But that, of course, doesn't quite make sense because you see there shouldn't be a Q here. Q represents the charge carried by an electron. And this was, of course, the charge current when electrons flow. Here, when phonons flow, they don't carry any charge. But instead, they carry an amount of energy h bar omega, which I should replace it with. So instead of Q, I should put h bar omega, except that I cannot pull it out of the integral because each phonon has a different h bar omega, so I need to keep it inside the integral. So I'll put that h bar omega here. So that's it. You see, just as with electrons, for elastic resistors, we had this expression for the current carried by electrons. In the limit of this, I guess, elastic phonons, that means we are assuming again that phonons go from left to right without exchanging energy, without losing energy, then we could write an expression like this. And you see, the translation was just very straightforward. We know, again, we have mean free paths, but now it's the mean free path of a phonon. What is this number of modes? With electrons, we know number of modes is about how many fit into the cross-section of your conductor. Here also, how many wavelengths fit into the cross-section. Here also, it's a question of how many wavelengths of the phonon fit into the cross-section. That's that. Instead of dE, we have dH bar omega. Instead of F1 minus F2, we have N1 minus N2, exactly the same thing. And instead of the Q here, we have put a H bar omega. Why? Because here we were talking about what is the charge carried by an electron, what is the charge current carried by electrons that are flowing. Here we are talking about what is the energy current carried by electrons that are flowing. That's it. And this then is the heat current carried by phonons. Now the next thing we need to do is, if we want to get a linear transport coefficient, then like before, we need to do this linear expansion. That is, how do we write N1 minus N2? So the approach would be that when I write N1 minus N2, it would be like partial of n with respect to h bar omega, with respect to temperature, times T1 minus T2. Okay. So instead of N1 minus N2 here, we'll put in something like this. And then we'll have a heat current that is proportional to the temperature difference. And the proportion, what is in between then, will basically give us the heat conductivity. So the way it would work then is, if we put that in, we could then write IQ divided by T1 minus T2. So that's like the heat conductance is equal to 1 over H, just whatever we have, integral d H bar omega m lambda over L plus lambda phonons H bar omega, and then we have del N del T. Okay. So now the question is, what is this derivative? We want to replace it, we want to find the proper expression for it. Okay. So now if you look at our expression for n then, again like before, let us take this quantity and call it x. So we have an x, that's like h bar omega over kt. So when you want partial of n with respect to t, what you get is, what you can write is dn dx times the partial of x with respect to t. And dn dx is this derivative of 1 over e to the power x minus 1. So you can see easily it is like e to the power x minus 1 whole square times e to the power x minus. So that's dn dx. And the partial of x with respect to temperature, that's this h bar omega over kt square. And I think there'll be another minus sign there, which you can cancel with that. So this is what you'd get finally. Okay? So if you use that, then I can put this back in here. Take this off. So now I'm going to write this quantity. That's this conductance. And then for partial of n with respect to t, that's what where we bring in this thing here. So we have another h bar omega over kt square, and then e to the power x over e to the power x minus 1 whole square, where x is defined as h bar omega over kt. That's it. So what we could do is, you'll notice, I could put a k squared here and put a k out here. And then this quantity is like h bar omega divided by kt whole squared. So this is like, I could write a x squared here. So this is then the expression for the heat conductivity due to phonons. Okay? Now, one interesting point in terms of evaluating these things I should mention is, I had said earlier that compared to the Fermi function, you see, this Bose function, the only difference is, while Fermi function looked like 1 over e to the power x plus 1, the Bose function looks like e to the power 1 over e to the power x minus 1. Now, on just looking at it, looks like a minor difference, but that of course means there's a major thing when you actually try to plot it, because when x is equal to 0, the Fermi function is just 1 divided by 2, that's half. So when I plot the Fermi function, if you looked at around x equals 0, so if this is x, around x equals 0, it will actually just go to half. That's the Fermi function. You know, x being E minus mu over kt. On the other hand, if you're looking at the Bose function meaning this one, the one that we're using for phonons, if you look at that, it will actually just blow up right here. Why? Because e to the power 0 is 1, and then 1 minus 1 is 0, so it just blows up. And of course, negative x doesn't mean anything. H bar omega has to be positive, so you only consider positive values of x. And the point is that it would blow up. So ordinarily what would happen is, if you are trying to evaluate something like this, you'd worry about this quantity blowing up when you try to do the integral. But because of all the other factors that have come in, you'll now notice that there's also an x squared here. And so this overall function doesn't blow up. Because when you put x equals 0, this goes to 0, but that also goes to 0, and the ratio stays fixed. because when for small x, actually this thing is like x squared. For small x, e to the power x minus 1 is like x. And so this is like x squared, and it just cancels out and becomes independent of x. So it kind of goes to a finite limit. So you can easily evaluate this quantity numerically, and this is what the theory would say then is about the conductivity, how you could find the conductivity due to phonons. And looks a lot like what we had for electrons, you see. If you look at what we had for electrons, it was something similar. G was Q over H integral dE m lambda over L plus lambda due to electrons. And then we had this del F del E factor. Right? That was what we had before. And this del F del E factor, instead of that, we now have this function. And if you look in the notes, I've discussed that the functions have kind of similar shape. See? Of course, there are differences, like the area under this function is 1. Area under this one, well, not exactly 1. So you actually need a numerical factor if you want to make it something whose area is 1. But they're roughly the same shape. And then you see the rest looks very similar. And the basic issue then is the heat conductivity due to phonons depends on the modes due to phonons, how many modes you have, what is the mean free path. When it comes to conductance, it is how many modes you have for electrons, what is the mean free path. See? And this gives you a sort of different viewpoint about this ZT product that I had mentioned earlier. You see, in the last module I said that the important figure of merit that everyone worries about with thermoelectrics is the ZT product, which is given by S squared G T divided by G plus divided by GK. And that is where I made the point that the GK is not just due to electrons, but you also have to consider the GK due to phonons. Okay? And often it's the phonons that are important, so you could kind of drop that. Now, we have a lot of thermoelectric materials which give you a Seebeck coefficient that is roughly of the order of K over Q. This is roughly on that order, K over Q. Like I discussed in, I guess, in one of these modules, that when you have a good thermoelectric material, it would be on that order, 100 microvolts per Kelvin, that order. Now, then what it is, what can we do to improve a thermoelectric? And the point is a lot of present-day materials are really limited by the ratio of this to this. That is, the conductance due to electrons compared to the thermal conductance due to phonons. Why? Because, well, the conductance due to electrons depends on m lambda. That is, how many modes due to electrons and what is the mean free path due to electrons. Similarly, for phonons, it's the m lambda for phonons. Now, when you compare electrons and phonons, typically electrons have a long mean free path, and that you think would help because that would make the ZT product big. This mean free path is better than that. And as you raise the temperature, usually that ratio gets better because the mean free path of phonons dies out very quickly often. But then, what goes against all this is the number of modes part of it. That often in these good thermoelectrics, in a given cross-section, number of modes is this idea of how many wavelengths fit into the cross-section. And the semiconductors typically have a wavelength of 10 nanometers to 100 nanometers. And so how many wavelengths fit in? You get a relatively small number. By contrast, if you look at the phonon wavelength, there you are often talking of 1 nanometer, something much smaller, which means for a given cross-section, you usually have a lot more modes. Why is the phonon wavelength different? Well, we'll go through this in a homework problem. It's a matter of looking at their, I guess, this omega K relationship, this omega K relation, and looking at, for typical energies, what is the corresponding wavelength. This we'll do in a homework problem. But the point is that with phonons, usually that M is much bigger, and that's what tends to bring down this ZT product significantly. whereas with electrons, the number of modes is much smaller. Well, couldn't you use metals? Because after all, metals have, the electron wavelength in metals is very short, because in metals, the electron has an energy that is, from the bottom of the band, it's much higher. So higher energy means, again, higher momentum, shorter wavelengths. That's this de Broglie principle. So that's true, but you cannot really use metals for making thermoelectrics. And the reason being just that when you look at this density of states, you see, E versus the density of states. As I mentioned, with metals, you are usually somewhere here. Whereas with semiconductors, usually you're somewhere here. So this is the electrochemical potential. And with semiconductors, what is involved is the number of modes here, and that tends to be relatively small. With metals, it's much bigger, but when you look up there isn't as much difference between above mu and below mu, and so overall you don't get much of a Seebeck coefficient. So an experimental fact is, while semiconductors would give you Seebeck coefficients that are 100 microvolts per Kelvin, with metals you'd get something much lower. And so even if you got a good conductance, the point is your Seebeck coefficient would be so small it wouldn't help a whole lot as far as the figure of merit is concerned. And that's why, although there is great interest in finding materials with good ZT, it has really remained a challenge for quite some time now. People have been looking at all kinds of things. They feel that by nanostructuring materials, by making small things, they should be able to get better ZT products. But that really remains to be seen where the field goes and what actually is achieved.